With the rise of vehicle electrification, more advanced and efficient systems are essential. IGBTs and silicon FETs were used in the electronics of most of the early hybrid and fully electric vehicles. These IGBTs maxed out with a switching frequency of around 20 kHz and silicon FETs maxed out around 100 kHz. These are being replaced by silicon carbide and gallium nitride switches, which offer higher efficiency and faster switching speeds. Silicon carbide can support switching frequencies of up to 650 kHz, and gallium nitride is more than 10 times as fast. Because these switches are so much faster, there's a need to monitor current and react to overcurrent conditions much quicker in modern electric vehicles. One common method to monitor current is to use a shunt resistor and measure the voltage drop across it to calculate the current flow. To reduce power consumption, a very small ohm value resistor is used. In this example, the circuit has 3 stages. First, measure and amplify the voltage drop across the shunt resistor. Second, compare the amplified voltage with the defined thresholds using a window comparator. And third, if the voltage falls outside of this range, a D flip-flop is set high, triggering a gate disabling circuit to shut down the system. A common requirement in systems using silicon carbide or GaN switches is to achieve overcurrent detection and shutdown in less than 1 microsecond. For these calculations, 1/3 of the response time is allocated to amplification. For an amplifier with a gain of 1 volt per volt, a bandwidth of just over 1 MHz is needed. Typically, these voltage drops across the resistor are small to minimize power consumption, so a gain of 50 volts per volt is common. This necessitates an amplifier with a gain bandwidth of 53 MHz. Current monitoring circuits like this are used in motor control applications. 3 separate current monitoring circuits can be used on the low side of an inverter to measure the current of each leg. This architecture provides the fastest response time and detailed current draw information. Another method is to use a single shunt to measure the overall current of the motor. This technique can save size and material cost. However, response time is slower and information on the current draw of each leg cannot be measured. Similar circuits are used in power delivery applications, such as in a 4-phase interleaved DC to DC boost converter typically found in electric vehicle onboard chargers. Current monitoring is critical in several electrified vehicle systems, including traction inverters, HVAC compressors, PTC heaters, DC to DC converters, and onboard chargers. To facilitate the design of current monitoring circuits, TI has created a high-speed current shunt monitor reference design featuring 4 different amplifiers. The input can be applied via a screw terminal or BNC connector, and the output can be measured from a test point or a BNC connector. 2 switches on the board allow for toggling between the different amplifiers so that the characteristics of each can be observed. Here, a 100 mV step input simulates an overcurrent event, and an amplifier configured with a gain of 26 volts per volt is used to amplify this signal to a level that can be used to trigger a window comparator circuit. When using the 50 MHz TLV365 amplifier, a total rise time of 0.4 microseconds is achieved. Now, when using the 100 MHz OPA354 amplifier, a total rise time of 0.21 microseconds is achieved. And finally, when using the 200 MHz OPA356 amplifier, it is possible to achieve a total rise time of 0.14 microseconds. TI's amplifier portfolio includes even higher bandwidth op amps that can be used to achieve even faster response times if necessary. At Texas Instruments, we develop industry-leading semiconductors to enable automotive engineers to create the next generation of electric vehicles. To see the entire portfolio of automotive qualified high-speed amplifiers, visit the link below.